different approaches for designing these kinds of algorithms. Briefly, we started out by talking about Monte Carlo approximation. After that, we talked about algorithms that work because they start at a random point that has favorable properties. And third, we talked about algorithms that make progress on average toward the solution. So at each step of the iteration, we reduce some kind of measure of error or potential on average, and as a consequence, the algorithm will eventually get where it's supposed to. So today we're going to talk about a different approach to designing randomized linear algebra algorithms, which is called dimension reduction. And this is one of the most familiar approaches to randomized linear algebra. This is often called sketching, although sketching is a term that has wider meaning and implications. So I want to be very explicit about what the role of probability is here. So the idea behind dimension reduction is that in linear algebra, we can use a random linear map to embed a high-dimensional linear algebra problem into a lower dimensional space where, while preserving the geometry, and the idea of this process is that by taking this big problem and squashing it, we will be able to arrive at a problem that's smaller and therefore faster to solve. Of course, on the other hand, we don't preserve the geometry of the problem exactly, so we lose something when we do this. And that's the downfall of these methods. And so they're only appropriate if you can afford what you lose. So I'll talk a bit more about that later. So have any of you encountered randomized dimension reduction before? Yeah? Tell me.
In random projections.
Yep.
I've seen that in the context of large-scale optimization problems.
Okay. So people have used random projections a lot in optimization too. In some ways it makes more sense in optimization because it's embedded in this framework where you make a mistake at every step, but who cares, you're going to fix it later. So some of the things I'm going to tell you about today don't have that character. You make the problem smaller, you solve it, you stop. Okay. Any other places you've seen random dimension reduction? Yeah, please.
I've seen applications in clustering.
Okay, applications to clustering.
I have, say, a large dimension data set. I squash it down to maybe 10 dimension, run k-means, and then I get the clustering.
Yep. And so, are there any theorems in this area that are familiar to you already? Johnson-Linden-Strauss. All right, I think that many of you know this, and that's what I was waiting to hear. So the Johnson-Linden-Strauss theorem from 1984 was the paper which was really concerned with metric geometry. But in the mid-90s, computer scientists realized that the ideas from this paper could be relevant to designing algorithms. So what did Johnson and Linden-Strauss discover? They said, suppose you've got some points in some high-dimensional Euclidean space. So here are some points. And there are capital N of them. And what they argued is that if you project these points down onto a lower dimensional space, you could still obtain a point set in the lower dimensional space that looks like the point set in the higher dimensional space. So what does that mean? What they were interested in was preserving inter-point distances up to a fixed distortion level. So the idea is that the distance between each pair of points here is going to be similar to the distance here after we've embedded the points into this lower dimensional space, and that is going to be true for every single pair of points up here. This one and this one, this one and this one, and so forth. And the number of dimensions that we need to accomplish this goal is only about the log of the number of points. This is maybe a little bit surprising. One way to think about this is sort of the maximum metric entropy of a set of endpoints. So there are applications, as I said, that arose in computer science in the mid-90s. So for example, the first applications were to solving large graph problems. And a more immediate application is nearest neighbor computations. So if you're interested in understanding, given a query point, which point in this fixed set is closest, doesn't matter if you do it up here or down here, right? Because you preserve distances. Okay. So the idea would be that you take your query point, you project it down here, and then you find the closest point in this low dimensional space, which you hope is going to be cheaper because these points have fewer coordinates. All right? So that's how approximate nearest neighbor algorithms work. A warning about this is that even though you can prove this theorem pretty easily, it's just some concentration inequalities, and many people know this theorem, I would like to warn you that this theorem is not actually very effective in practice, in the sense that if you really care about preserving the interpoint distances, you need a very high dimensional space. It's maybe just a constant times log m, but that constant is big. So the distortions here are really pretty substantial, and so you should be careful using this result in practice. It's very easy to see this if you start doing numerical experiments. Yeah.
How do you quantify distortion?
I'm going to talk about it in a minute in a different context. Yeah. Distortion is just how much you can stretch or compress a distance between a pair of points. But it's uniform over the whole set. That's the thing that is hard to get. So if you picked a random pair of points, the distortion is not bad, but the worst case distortion can be pretty big.
But somehow it should be defined by ratios of distances.
Yeah. 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 Mm-hmm. Yeah, exactly. Okay. So this is not really about linear algebra. This is just a result that many people know, and it gives you some intuition for what might be possible. And so we're going to talk about another kind of diminishing reduction theorem. And for this, we need to introduce the definition of a subspace embedding, which was crystallized by Carlo in 2006. So here's how this works. We're going to be interested in not a point set anymore, but actually an entire subset of Rn, a linear subspace with dimension d. Okay, so now instead of discrete points, we have an entire subspace L. You should be thinking the dimension d here is a lot smaller than the ambient dimension. Okay, and suppose that phi is a S by N matrix with the property that we have an eraser here. So suppose phi is a matrix with the property that if you use it to embed a point from the subspace L into this S-dimensional space, so you start out in Rn, you're moving down to Rs, and you would like the Euclidean norm of the point to be preserved up to a factor of 1 plus or minus epsilon. And you would like this to be true for every single point in the subspace. So the picture here is something like this. You're in some high dimensional linear space up here. You've got a low dimensional subspace. You have this map phi that takes us down into a lower dimensional space Rs. And the hope is that for every point here in the subspace L, its distance from the origin is about the same after you project it down. So to recap, you're taking a subspace in high dimension, you're squashing it down to a subspace in a lower dimension, and the hope is that the magnitude of each point in the subspace is approximately preserved under that embedding. All right. If this is the case, then we say that phi is a subspace embedding for the subspace L with embedding dimension S and distortion epsilon. So this is now the rigorous definition of distortion in this context. Okay? So pretty simple thing. So any questions on the definition? This is going to be the central thing today. Okay. Is this possible? Do these things exist? Okay, well, it probably depends on the relationship between S, the embedding dimension, and the subspace dimension, right? So what do we know about the embedding dimension as it relates to the subspace dimension? Yeah, S had better be bigger than D, right? So we absolutely need S greater than or equal to D. Otherwise, we're going to have to send something in the subspace to 0 because it's going to take up more than all of Rs. All right, so that's bad news for us. So we need the embedding dimension to be bigger than the subspace dimension. That makes sense. Is there a subspace embedding with embedding dimension D? Sure. All you need to do is take the map whose kernel is L perp. Okay, so you just take a map that acts on L and maps it to the entirety of Rs. Okay, so you can think about Rs as being isomorphic to, okay. So for sure you could do this just with a projection. So that's good news. The thing that we are going to want to do is to build one of these things without knowledge of L. So we'll talk more about that in a minute. Okay, so we want to be able to do this without assuming that we have a whole lot of information about the subspace in advance. All right. Another comment What does this have to do with Johnson-Lindenstrauss? So Johnson-Lindenstrauss asserts that there is a linear map that reduces the dimension of a point set in the sense that interpoint distances are preserved. And in fact, the same thing is true here. So for all points x and y in the subspace embedding ensures that the inner point distances are preserved after embedding. Okay, so this is the distance between the embedding of x and the embedding of y. And I'm asserting that that distance is about the same as the original distance between x and y in the subspace here. Okay, why is that? Sorry, I'm standing in front of the equation.
X minus y also belongs to.
Yeah, x minus y belongs to L because it's a linear subspace, and the map phi is linear. Okay, great. So this really is a metric embedding in the sense that Johnson and Lindenstrauss were studying. Okay, now I want to say one more thing about these embeddings to connect this with matrix analysis. So suppose that we actually have the subspace L represented as a matrix. So suppose that L is the range of a matrix U where U belongs to R n times D, and U has orthonormal columns. Okay, so U is a matrix with orthonormal columns, and those columns form an orthonormal basis for the subspace L. That's what this statement is saying. So the claim here is that phi is a subspace embedding for L if and only if we have the following property. So we're going to think about applying phi to the matrix U. Right? So the range of this matrix contains every vector in L. And so this will tell us something about the action of phi on the whole subspace. And what do we need to happen? We need the minimum singular value and the maximum singular value of this map to be under control. Obviously, the minimum is always smaller than the maximum, I think. And what do we need this to do? We need the maximum to be smaller than 1 plus epsilon and the minimum to be bigger than 1 minus epsilon. So we can actually convert this question about subspace embeddings, this geometric notion, into a question about the interaction between the embedding map phi and a matrix that describes the subspace. And so that matrix that describes the interaction needs to be very close to an isometry. So the matrix VU can't stretch anything by more than 1 plus epsilon, and it can't contract anything by more than 1 minus epsilon. Okay? I'm not going to prove this. It's a short exercise for you in linear algebra. But this is the way that we get our hands on explicit subspace embeddings, by checking this condition. All right. Any questions on the definition, connection with metric embeddings, or the proposition about the spectral interpretation? All right. Yeah?
Are we going to need to access to either U or some characterization of L later?
Great question. So that's the next thing we're going to talk about. Where do we get these things? Can I write over here? Okay. So how can we construct a subspace embedding What if we don't even know L? Okay, this seems crazy, right? Like, how are we going to embed this subspace if we don't know what it is? So the idea, which should be obvious in this context, is to do what? Choose phi to be random. Okay. So we're going to choose phi to be, whoops, I got the dimensions backward. Choose phi to be a random matrix. And then we are going to hope that it serves as an embedding for a fixed subspace L. It's sort of clear that if you choose some fixed matrix phi, there are going to be subspaces that it can't embed, right? Because you could go looking for vectors in the kernel and put those in your subspace, and then those vectors get annihilated. Okay, so to reiterate, for a fixed phi, there are subspaces that it cannot embed. So no deterministic construction can work for every subspace. And the cool idea here is that instead, if you think about the subspaces being fixed and you choose phi at random, even without knowing anything about the subspace, you might still be able to obtain this property. Okay? So that's going to be our goal. And the first thing I want to demonstrate is that this is possible. What we are going to lose is that we're not going to get S equal to D anymore. It's going to have to be bigger. And we're also going to have to pay for the distortion. We can't get away with epsilon equals 0, which we could if we used full knowledge of the subspace and we were willing to do some work. Okay. So I'm going to give you two examples. The first one is a Gaussian embedding. And Gaussian embeddings are mathematically elegant. And there is a lot of theory about Gaussian matrices that allows us to understand why they serve as subspace embeddings. Unfortunately, they're not very friendly computationally. You have to draw a lot of random variables and store them, and then you have to multiply by this big dense matrix. And so after that, I'm going to describe a second example, which is called a subsampled random trig transform, which I'm only going to describe at a very high level, but addresses the computational issues. All right? So that's next. So let's check that we can design an oblivious subspace embedding, one that does not care about the identity of the subspace and still is able to produce an embedding. Okay. So Gaussians. All right. So we're going to fix an orthonormal basis U for a subspace once and for all. So the subspace is frozen, and now it's our job to build an embedding. Okay, but we're going to pretend that we don't know this guy. He's hiding behind the curtain. All right, so we're going to draw a matrix phi of dimension S by n with IID, independent identically distributed, normal entries that have variance 1 over S. Okay? So this maps into S dimensions, and I have a normalization here that depends on the embedding dimension. This is not so important. It just is a scaling property. And what does that scaling property get you? The scaling property tells you that if you take a fixed vector and you reduce its dimension with this Gaussian matrix, on average, you preserve the norm of the vector. And this is true for all fixed x in Rn. Okay. So this is an easy calculation that you should perform for yourself. So what this is telling us is that at least for one vector, the Gaussian matrix preserves its squared magnitude on average. So that's good news. That's what the 1 over s gets you. And that hints that it's got the right normalization potentially to embed more vectors. Okay? And of course, the more vectors we have and the fact that we don't want an expectation anymore means that we're going to have to pay something. That's where the distortion comes in. So this says the norms are preserved on average. And now, to check whether phi embeds the range of U, we're going to use the spectral property. Okay? So we're going to use this condition to evaluate whether or not phi is an embedding. So remember that Gaussians are rotationally invariant. And what that means in this context is that the matrix phi times U, which is of dimension s times d, is obtained by projecting this Gaussian matrix down from n dimensions to d dimensions. So we're reducing the right-hand dimension of this matrix, but we're doing this with an orthogonal map, an orthonormal map. Okay? And because Gaussians are rotationally invariant, they still have the same distribution even after you combine these guys. And so in fact, this is still a matrix with IID normal entries with the same mean and variance. Okay? It's very important that U is orthonormal in this context. We've used the same fact before when we studied the randomized SVD and some of the other algorithms we talked about. Okay, now, because this combined map, which describes the interaction between the subspace embedding and the basis for the subspace, because it's Gaussian, we can just break out theorems about the behavior of Gaussian matrices. This is a very simple Gaussian matrix, so we don't need to work very hard. There is a well-known theorem, which has maybe a long history, but appears in a paper, usual references, this paper of Davidson and Sharek from 2002. And it states that we have the following probability bound. The minimum singular value of this Gaussian matrix, of course, is smaller than the maximum singular value. How small could this be? Well, it's about 1 over root d over s. So here's the number of columns. Here's the embedding dimension, the number of rows. And we maybe lose a slop factor here. So this is a parameter. And on the other end, we want to know how much this matrix stretches things out. Well, the right answer is 1 plus the aspect ratio, square root. And again, we have a slop factor. And the probability of the singular values of this Gaussian matrix falling outside of this range is exponentially small. It's like e to the minus s t squared divided by 2. So it is extremely unlikely that you're going to see a constant distortion beyond this level. Okay. So heuristically, if you look at the singular values of a Gaussian matrix, they have support between 1 minus the aspect ratio and 1 plus the aspect ratio, and this theorem describes the probability of the singular values falling outside of this range. Yeah.
Greater than 1 minus?
Oh, sorry, where?
Greater than 1 minus?
Oh, sorry, failure probability. I always get this backward. It's written right in my notes, but yeah, thank you so much. What else? I know every time people are looking at me funny, it's because I wrote something wrong on the board. Should have learned this by now. Okay, any questions about what this statement says? Yeah.
So eventually we want S to be small, right?
Yeah, we want S to be as small as possible. I'll explain what this means practically in just a second. Just want to make sure that it's clear what I've written here and that there aren't any more mistakes. All right, so. Wow, yeah. Thank you. What else? Okay, good. So what does this mean practically? It means that we have the heuristic that if we take S to be approximately d over epsilon squared, we get distortion epsilon. All right, so I'm basically taking advantage of the fact that this failure probability is so small that you could basically just think about t as being 0. Okay, it's a little hand wavy, but practically speaking, this is what you'll see. Okay, so if you want to embed a d-dimensional subspace into S dimensions, you need to take S to be d over epsilon squared to get distortion epsilon, okay, in this formula. And the way to understand this is that for a fixed subspace, you draw a random map, and then it is very likely to have this property. Okay? And what we're going to do, I'm going to repeat this again later, is we're going to assume that this property holds, and then everything after that will be deterministic. Okay? So the whole point of the randomness here is to ensure this spectral property, which guarantees a subspace embedding. And to obtain this condition, it's practically speaking enough to take the embedding dimension to be proportional to the subspace dimension and inversely proportional to the square of the distortion. Okay, yeah?
So we don't know U, but is it like reasonable to know D?
Yeah, so you'll see in the examples that we do know D. And on some level we know U, it's just we have to calculate to get it. And that's what we don't want. We're trying to avoid computation here. So you'll see how this goes in a little bit. So we often assume that we know D or have some bound for D when we do this. Okay, so where did we see this 1 over epsilon squared before? Monte Carlo, yeah. It's not a coincidence. And what did we say about the reasonable range of epsilons in the Monte Carlo world? Yeah, we want epsilon to be pretty big because we pay very heavily when epsilon is small. So if epsilon, so practically, we need to take epsilon to be like 1 over root 2 or like 1/2 or something like that. So pretty bad distortion. Because otherwise, if you wanted to take epsilon to be like 0.1 or something, you're going to pay a factor of 100. And at that point, you've eliminated any benefit from doing this kind of thing. Okay? So these subspace embeddings, whenever you use them, you should be thinking, I have to be able to accept a very high distortion. Otherwise, they're just not appropriate. We'll see how this plays out in the algorithms later. And on some level, what's really important here is that the subspace embedding doesn't send anything to 0. Okay? So it's really this lower bound that's somehow the critical piece. We don't want to kill off any vectors that we care about. Okay, great. Any questions about why Gaussian matrices are oblivious subspace embeddings? Did any of you take high dimensional probability from Vladimir or Galina? No? Okay. Just curious. So they probably talk about this theorem in their course. Okay. Now, I want to describe another subspace embedding, which is more useful for some practical applications. It is one of many. It's just the one that is easiest to describe and to quantify the behavior. So these are called subsampled randomized trigonometric transforms. They were proposed by Ilone and Chazelle in 2006. The journal version's a little later. And here is a description of a subsampled randomized trig transform for use in this context. So it is a product of 3 matrices, which I will describe in a second. These 3 matrices have dimensions s by n by n, and n by n. The first one is an orthogonal discrete cosine transform matrix. So it's like a Fourier transform, a DFT, but this is a real version. So what do we know about FFT matrices? Can we apply them to vectors? Yes, and we do that using an algorithm called the fast Fourier transform. And so it is very easy to apply this matrix, okay, using a fundamental algorithm attributed to Gauss. So we can take an FFT, which spins things around. We multiply by a diagonal matrix, which has entries epsilon 1 up to epsilon n, where the epsilon I are independent Rademakers. So these all have magnitude 1. So this is an orthogonal matrix. And this scrambles things up. Oh, I got these backward. Why do I always do this? This one is F. This one is D. Yes? No? Yes, it's the other way. So first we scramble things up by putting on random signs. Then we rotate into some other basis. And because everything has already been randomized, there are no relations here that are left. And so you wind up with these vectors being smeared all over the place. Okay? So the combination of the randomization followed by the trigonometric transform makes any fixed vector come out the other end with as a flat vector whose entries are about the same size and have different signum. And this last matrix R is a restriction to S random coordinates. So it just takes the output here and picks S entries and ignores the rest. The idea being a vector whose entries are about the same size, you can estimate its magnitude by any subcollection of its entries. Okay? Because when the entries are all about the same size, each entry sort of has its share. So that's roughly what's happening here. Okay, it's not so important to understand why this works. I was just trying to give you a little bit of intuition. The point here is that it's cheap to multiply by a diagonal matrix, it's cheap to apply a Fourier transform, and then it's cheap to ignore some of the coordinates. And so you can prove that it is sufficient that S is bigger than about d log d to get distortion epsilon equal to 0.6. And then you can write down the constant. It's like maybe 4 or something. So the point is that if you make the embedding dimension a little bit bigger than the subspace dimension by a logarithmic factor, you can get a constant distortion with this map. And this is, let's say, with reasonably high probability. And the key benefit of this is that the cost to apply to a vector is order n log n operations. Okay, because all we're doing is flipping signs of the vector, then we're computing a fast trig transform, and then we're ignoring a bunch of coordinates. So it's very, very cheap. And that means that we can use this as part of a computationally efficient procedure to reduce the dimension of vectors. Yeah, Monte.
Coming from someone who doesn't know FFT,
Yeah.
if I know that I'm only going to take, say, the first 10 coordinates,
Yep.
is this something I can use to accelerate the multiplication by f?
Yeah, you can get n log d. In fact, you can do that regardless of what the output coordinates are, but it requires a special implementation. Yeah, more questions? Yeah.
Is R random?
Yeah, R is random. You choose S random coordinates from the vector, but that's fixed, right? So you draw this matrix at random and you fix it, and then the claim is that with high probability, it is a subspace embedding with constant distortion and embedding dimension, provided the embedding dimension is at least this big. Make sense? Okay, good. Any more questions on this example? Yeah, two.
There's something I don't get.
Yep.
Isn't d log d bigger than d?
Sorry, one more time?
Isn't d log d bigger than d?
Yep. That's good because you don't want the embedding dimension to be smaller. It would be better if this logarithm weren't here, but this is what you can prove. And in fact, the logarithm is necessary in the worst case. Practically speaking, you don't see the worst case, and this kind of scaling is still valid here.
Okay, so
Yep.
the one thing I don't fully follow
Okay.
is we start from a space that is d-dimensional.
No, we start from an n-dimensional space.
Okay, because we don't know the exact...
That's right. You think about, so if you look at the Gaussian example, we have a subspace of dimension d in an n-dimensional space, and we'd like to reduce that dimension n to the embedding dimension s. So s has to be bigger than the subspace dimension d, but what we really want is it to be a lot smaller than n. Okay, that's the goal here. We want an output who, an embedding that does not depend on the ambient dimension, only on the subspace dimension. We have achieved that here, and we've achieved that here. So you see that the embedding dimension doesn't depend on the ambient dimension of the vector at all, of the subspace. Okay. Make sense? More questions? Mm-hmm.
Do you ever check? Like, I mean, I know we assume that we don't know what L is.
Yeah.
At some point, is there a way to,
Okay.
check or something?
So 2 comments. First of all, these things work with high probability for any fixed subspace. So if you choose one of these things at random, there's a pretty good chance it works, and you don't need to investigate farther. The other question that you can ask is, what if you do know something about L? In that case, you could be more creative about how you design these maps to take advantage of that. Yeah. So there is some work on that, but part of the goal here is to avoid calculations involving the subspace if you can help it, because it takes work to figure out what the subspace is and how it's sort of arranged inside the larger space. These maps, they don't care. There's no subspace here in this construction. There's no subspace here in this construction. It's just a very simple random matrix. Okay. Well, this one's simple. This one's a little more complicated, but it's designed to be computationally efficient. So I just wanted to give you some evidence that it is possible to design one of these things as computationally efficient. But the key point is the random matrix has nothing to do with the subspace. And it still works almost all of the time. Okay. More questions? Yeah.
How would you know that this matrix will work with some probability? How would you know that? So is it cheap to investigate if my matrix is good?
Is it cheap to investigate whether it worked? I mean, so you can see that investigating whether the matrix worked would involve you having a basis for the subspace and involve computing minimum or maximum singular values. So that's not what you want to do. So what you want to do is draw the random matrix, assume that it works, and proceed forward. Later in the computational pipeline, you might discover that it did not serve your purpose, at which point you would go back. But you don't want to check this property explicitly because it is potentially expensive. Okay. But the theorems guarantee, in this case, extraordinarily high probability of success. Here, pretty high probability. Practically speaking, these things essentially always work. So it's not really something that you should sweat too much. Later, after you solve the problem, you should maybe check whether you got the right answer or not. And if you didn't, then try again. So this is posterior error estimation. I'm not going to talk so much about that, though. Okay. So let me summarize what's going on here, and then we'll do a couple applications. So summary. We have a fixed subspace, L, which is the range of some matrix U with orthonormal columns. We construct a random matrix, phi. So L is a subspace of dimension D in Rn. We construct a random matrix phi, which is S by n. In practice, if you choose the embedding dimension to be d over epsilon squared, you get distortion epsilon. This is rigorously true for the Gaussian, and empirically it's usually true here. And this is true with high probability. So you can apply an SRTT to a vector in order n log n operations. So we can apply these transforms to data very efficiently. And the idea is that you draw the matrix at random, you fix it, and then you design algorithms that work conditional on the subspace embedding property. Okay, so what's happening here is that all the probability here is in the construction of the embedding map. After that, you assume that you are successful, and you use the subspace embedding condition to design algorithms. Now, it's possible that you screwed up, in which case your algorithm will maybe give you the wrong answer, and then maybe you have to go back to the beginning and try again. All right. Questions on this paradigm? I haven't shown you any applications yet. I need to justify why this is interesting, but it's important to understand that the randomness is here, and then after that, the algorithms are deterministic. All right. So I'm going to describe two applications to you. All right. And the first one is one that already appears in Charlot's paper. So this is called approximately squares. So our goal is once again to solve an overdetermined least squares problem. Where A is a tall matrix. Okay, so once again, highly overdetermined least squares problems. And our goal is to try and solve this problem faster. And as with the randomized catch-marks method, remember we didn't really need all the equations, right? It's because they're kind of redundant with each other. And so the hope is that there might be some way that we could squash this matrix A and still retain enough information to solve this problem. Okay. So we're going to assume that A is dense and unstructured. So it's just some complicated, yeah.
So your A is n times B, right?
Oh yeah, sure. Another typo. Thank you. M by D. Thank you. Okay. A doesn't have to. Yes, so many typos. I'm sorry. So A is not orthonormal. Okay, it's just some data matrix or something. It's handed to you by someone who wants to solve a least squares problem and says, "Can you please help me?" Okay, we're going to assume that A is dense and unstructured, so we're not going to place any additional assumptions on it. And so to solve this problem directly, how much does it cost? How do we do it?
Directly?
Yeah, what's the direct method for this problem?
Cholesky?
Not Cholesky, because A is not positive semi-definite.
QR?
We do a QR decomposition, and then we project B down onto the range of Q, and then we solve a triangular system. So this is an order D squared n cost for the direct method. Okay. So this is how people would have solved this problem historically. It gets you the exact answer, but it's effectively got cubic complexity. Okay. Fortunately, the quadratic part is a small dimension, not the big dimension, but that's the goal. And we're going to get a solution X star, which might or might not be unique, depending on whether A is injective or not. Okay. Now, how could you use a subspace embedding to solve this problem? So the idea here is that we are going to squash the large dimension n down to the embedding dimension s, while hopefully preserving the geometry of the least squares problem. So this is called sketch and solve. And it has 3 steps. First of all, we are going to construct a random matrix with a fast multiply that serves as a subspace embedding. For what? It's going to be a subspace embedding for the range of A augmented with the column B. Okay, so we want to be able to preserve all linear combinations of the columns of A and the right-hand side B. Okay, so we're going to construct a subspace embedding phi that works for this subspace. Doesn't matter whether we know the subspace or not because we can just draw phi at random. And moreover, we can do so in a way so that phi has a fast matrix vector multiply. But all the randomness is here. We assume phi has the subspace embedding property for this subspace. Then we continue. That makes sense? All right. Now, what do we do with this? We sketch the data. This is the way that it's usually termed. And what that means is we are going to apply phi to the matrix A to get an S by D matrix. And we are going to apply phi to the right-hand side to get an S vector. And the cost of doing this is n log n for the vector and dn log n for the columns of the matrix. Okay. So this is order dn log n because we've assumed that phi can be applied to vectors efficiently. And we are doing that to B. We're doing that to the columns of A. All right? And so this is a total of D plus 1 vectors, each of which costs us n log n. Questions on this? OK. Now, we solve the problem, minimize over x in Rd, 1/2, phi ax minus b, to get a solution x sketch in Rd. Okay? So we've collected the data for this least squares problem. We're going to solve it. How do we do that? We use a direct method. But now the number of rows is not n anymore, it's s. So the cost of doing this is not d squared n, it's d squared s. So we've chopped n down to s, and s doesn't depend on n. Okay, so this is good. And the output is a vector x sk, x sketch, and we hope that x sketch is an adequate solution to the least squares problem. That's why it's called sketch and solve. You squash the data, you solve the problem, you declare victory. I should warn you that this doesn't actually work in practice. I'll explain what is true and what the issue is in just a second. Although there are a lot of people who write papers about this, who shall remain unnamed. It's a very beautiful idea, though, and it is actually very useful as a subroutine in other procedures, but by itself, it's maybe not a great way to actually solve least squares problems. But I think that as you know, a student of this subject, it's important to understand that this is a one of the basic applications of subspace embeddings. All right. So any questions on the procedure? So let's summarize the cost. So the cost of the sketching, as I said, is order dn log n. The cost of the solve is order d squared s. And if you use the heuristic that s is equal to d over epsilon squared, the total cost is order dn log n plus d cubed over epsilon squared. Okay, so I've just written down the s and added these two numbers. And this should be compared with the direct method, which, as I said, costs order d squared n. So where do we win here? Here, this cubic term, we've replaced n with d over epsilon squared. If epsilon's like 1/2, that's fine. Here, in this first term that comes from the sketching, we've replaced one of the d's with a log n. Okay? So when do we win? We win if log n is a lot less than d is a lot less than n. So there's this sort of funny regime where d is not too small, but it's also a lot smaller than the ambient dimension, where this is going to be faster than solving this by the direct method. Now you may wonder, how do we do? So there is a very elegant analysis, which is essentially due to Charloche. So with everything as above, the residual in the sketch solution for the original matrix and original data, right? So as I said, you want X sketch to be the proxy for the true solution here. So you'd like to know what the error is. What's your residual? So we need to compare that with the optimal residual from an actual solution to this problem, say X star, the one that I nominated before. So how much do you lose as compared with the optimal? You lose a factor of 1 plus epsilon over 1 minus epsilon, where epsilon is the distortion of the subspace embedding. Okay. So a couple comments before we prove this. So the residual in the sketch is comparable with the optimal. And so if, for example, epsilon was 1/2, then the loss on the right-hand side is a factor of 6. So for epsilon equal to 1/2, it's 3 divided by 1/2 is. So you only lose a factor of 6. Okay, not so bad, because maybe you could solve this problem a lot faster. Great. The unfortunate feature of this, however, is that it's not so clear when you can afford to lose a factor of 6. So how big is the optimal residual? We don't really know, do we? So it depends a lot on the situation where you're doing this. So if, for example, you have a data fitting problem where you've got a whole bunch of data points and you're trying to fit a line, you make an error in every one of these points because they're noisy. So the residual is huge for data fitting problems. So do you think that if you multiply the residual by a factor of 6, you're going to get the same line? Yeah, maybe not. Okay, so for data fitting problems, this is a really bad idea. A factor of 6 excess error is intolerable. On the other hand, you can imagine another situation where the picture looks more like this. Okay, you can't see that. Where the picture looks more like this. You've got a line, and you've got data that is basically right on the line. So the residual is, say, 10 to the minus 8. In that case, if the residual is 10 to the minus 8, maybe you can afford to multiply it by 6 and you're still happy. Okay? So this actually happens in some kind of linear algebra problems where the matrix A is cooked up in some special way. So this is not insane. But this is a good situation where you can afford the loss. This is a situation where you're going to have to work harder. Okay? Yeah, Matteo.
How does all of that compare to just selecting a random subset of the rows in A?
Yeah,
solving that?
Yeah, that doesn't work in general because you could, for example, pick rows that are 0 or rows that just aren't that relevant. So somehow you need to mix the rows together so that you aggregate the information in the equations. That's what these sketches are doing. They're really like scrambling things up so that all of the equations, the S equations you have left, carry information. There are some situations indeed where you can sample rows at random and still be confident that they carry information, but you require a lot of assumptions on A to be able to do that. People also try and construct adaptive distributions for sampling the rows, which is expensive and highly variable. But there are some situations like active learning where this might make sense. Anyway, so a lot to say about this. Okay, more questions? Yeah.
More of a comment. So my understanding of this, I'm an optimization person, so
Yep.
I see all that as optimization problems.
Hmm?
We start from a certain least square problem,
Yep.
and then instead of solving that, we
Yep.
solve the number problem
Yep.
with a different matrix.
Yep.
And we solve the smaller problem to optimality,
Yep.
which was probably the wrong idea because we were solving the wrong problem.
No.
So going back to the middle pane where we say we design algorithms that work conditional on subset embedding property, there are algorithms that take into account the fact that we might have the wrong problem because
Yep.
of the random embedding,
Yep.
and are designed to be robust to that
Yep.
in some way.
Let me tell you how I would like to think about this in the optimization setting. What I would like to think about is that this is a subproblem in a bigger optimization scheme. You solve it, maybe to optimality, maybe not to optimality. You make some progress. You do it again. Okay? So this is a paradigm, right, where you are making progress on average. The average on average is over the choice of the random subspace embedding. Each time you apply it, you get a little bit better. And so as you say, man, it doesn't matter if you solve it to optimality. So any progress is good, and eventually you will get where you're going. There are other ways to use these ideas to design more efficient algorithms. I just don't want to go down that road because it's more complicated story. Yeah, more questions? Okay, so let me write down the other thing I just said quickly, and then this only makes sense for large distortion epsilon because otherwise the cost is too high. And the implication here is that it only works well if the residual is tiny. All right, so this picture versus this picture. And one other warning, small residual is not the same as solving the problem. Okay, so roughly, you have to keep in mind that if you want to know whether X sketch is close to X star, you have to pay for the condition number of the matrix. Okay, so even if the residual is small, doesn't matter if the matrix is badly conditioned, you might still get garbage. So something to be careful about whenever you see a theorem that tells you about residuals. X sketch might have nothing to do with X star if A is badly conditioned, even if the residual is small. So beware. All right, good. Any more questions about the sketch and solve approach? Yeah.
So this result is basically saying that if the solution to this least square is 0, you pay no money.
Yeah, that's a great observation. So if this is a consistent system, so the equations can be satisfied exactly, the optimal residual is 0. 6 times 0 is 0. So you're very, very happy in that situation. There are some settings where that seems to occur. Yeah. And in that case, these methods are a win-win. Yeah. Great. More questions? Yeah.
Maybe in the optimization setting you're
Yeah.
mentioning, so how do you know you're making progress in average? Like presumably there's some adaptation, right?
Yeah, so what happens is that you are typically iteratively refining a solution, right? So you've got a new solution, you try and solve a new subproblem. On average, it works, and even if sometimes it doesn't work, it doesn't matter because eventually the average is a win. So Like
But
one of
if
these.
you keep choosing the same, or like you choose the same random matrix, the same procedure,
Okay.
right? Basically.
It depends. So there are two ways to think about it. One is that for the optimization problems, typically people choose a different random matrix every time. For linear algebra problems, you can choose one subspace embedding at the beginning and never do it again, because in fact, you don't make progress on average, but you are guaranteed to make progress conditional on the subspace embedding property. So if it's a subspace embedding, at every step you do better. Conditional on it being a subspace embedding. So, yeah. More questions? Okay, let's talk about one more example, and then we're going to wrap up. Okay. Okay. Oh, I forgot to prove the theorem. I'm sorry. Let's prove the theorem. By the subspace embedding property, we know that the residual induced by the sketch solution is comparable with the sketched residual because phi is a subspace embedding for the range of the concatenated matrix AB. So no matter what X sketch is, this is a linear combination of the columns of A and B, and so phi preserves its norm. There's no probability here. Okay? Phi preserves this entire subspace, and therefore we get this comparison, regardless of what X sketches or the fact that it depends on phi and A and B and everything else. Okay? So this is one of the reasons that we want to evict all the probability from the proof. This is a deterministic statement, conditional on phi being a subspace embedding. Now, we chose X sketch to solve this optimization problem, right? So X sketch is the optimal point of this problem. So that means that if you replace it with any other vector, the situation gets worse. That's what optimality means. So why don't we pick X star? So I have used optimality of X sketch to replace it by X star and to make the residual in the sketch problem worse. What do we do next? We undo the subspace embedding. Okay, so now we just get rid of phi. Again, this is some linear combination of the columns of A and B. We don't know what it is, but it doesn't matter because the subspace embedding is valid for the entire subspace. And so we get the comparison between the optimal residual and the sketch residual. Okay. This is actually a very common pattern of proof and these kinds of methods where we cleverly exploit the optimality of the proxy problem. Okay, any questions on this? Yeah.
If phi is exactly orthonormal,
Mm-hmm.
then we do nothing.
Yep. If it is orthonormal and this is not contained, sorry, if the subspace doesn't intersect the kernel of phi. So if it is a subspace embedding and it is orthonormal, no, orthonormal is not enough actually. So you can construct these randomized trig transforms are partial orthogonal matrices, and you still have a distortion. So it's not enough. Yeah. Okay, let's do one more application. So it's in a similar spirit, but it's a problem that somehow looks a bit different. Application 2 is what we call approximate null space. So this work is due to Anna Gilbert, and it was revisited by Park and Nakatsukasa last year. So here's the problem. Someone hands us a tall matrix. And our goal is to find a subspace W that captures as little energy as possible from A. So we write this optimization problem as minimize over W transpose W equal identity of dimension K. So this ensures that the columns of W are orthonormal. And our job is to find the orthonormal basis that evades A as much as possible. Okay? So if A actually had a null space, this would go looking for the null space. In a lot of computational problems, the matrix A almost has a null space, but it actually has some small singular values that are not 0. And you're trying to find those directions. Okay? So we call the solution W star, an approximate null space of dimension K. It is used in a bunch of applications. One of them is total least squares, which is also called errors in variables regression in the statistics world. So this is regression where instead of dropping straight down the line, you drop at a right angle to the regression surface. So you need to solve this problem for TLS. It arises in the music algorithm for spectral estimation. It arises in the AAA algorithm for rational approximation. So there are tons and tons of situations where you need to do this. And the cost of doing this directly is essentially computing an SVD of A, which is a d squared n operation. All right. Now, one of the cool things about this problem is that the value of the optimal point is the sum of the smallest squared singular values of A. Okay. So this is the sum of the K smallest squared singular values of the matrix A. And the hope here is that those are tiny, tiny numbers, because we're hoping that we're finding stuff that's aligned with either the null space or something that is pretty close to being a null space, like vectors that get destroyed by A. Okay? So the value of this problem is very small. Okay. And the classical approach for doing this would have been to compute a thin SVD of A and to pick off the smallest K right singular vectors. All right, good. So let's develop a sketch and solve approach for solving this problem. So this idea dates to Anna Gilbert's paper. How does it work? So, step 1, construct a random, fast subspace embedding phi for the range of A. So we know the range of A on some level, but we don't want to have to orthonormalize the columns because otherwise we'd have already solved the problem more or less. So that's why these random subspace embeddings are cool. They allow us to reduce the dimension without actually knowing a basis, an orthonormal basis for the range. Second, we will sketch the matrix A. So we'll compute phi A, which is now a small matrix of dimension S by D. The cost for doing this is typically about dn log n. And third, we will solve the sketched problem, which is minimize over W star W equal the identity. So matrices with k orthonormal columns. And we will go looking for a matrix W that solves this squashed minimization problem. The cost of this, again, is computing an SVD, but we're now computing an SVD of a matrix with far fewer rows, so the cost is going to be d squared S instead of d squared n. Right. And we obtain a solution, W sketch, and we hope that it's a good approximate null space. Okay, so we hope that the solution of this problem serves in place of W star, the solution to this problem. Okay, this is the sketch and solve paradigm. Okay, so the total cost is order dn log n plus d cubed over epsilon squared. And when the embedding dimension S is d over epsilon squared. And so, once again, this should be compared with the cost d squared n of the direct method. And so we win in exactly the same context when log n is smaller than d is smaller than n. All right, now we can analyze this method. So this result is effectively due to Gilbert et al. So as above, we would like to compare the value of the objective at the sketch solution with the value at the optimal solution. And what is the comparison ratio? It's 1 minus epsilon reciprocal times 1 plus epsilon. Same constant as before. And so what's happening here is that we're finding out that this sketch subspace carries not much more energy than the best approximate null space. Now, how does this differ from the situation with the least squares problem? We're really explicitly going to look for a subspace where this objective value is tiny. That's the goal of the problem. If all is right in the world, the value of this problem is extremely small. You found something that looks like a null space. And in that case, maybe you don't care if you inflated it by a factor of 6 because it was a null space. And in fact, if W star is actually contained in the null space, the value is 0, and the sketch solution is exact. So that makes us happy. All right, so you're a little ahead of me. But, all right, how do you prove this? Same. We don't have to do anything different. We just change the objective function. Okay, great. Any questions on the approximate null space problem or the sketch and solve approach? In the back.
So let's say I don't want to null space. Maybe I just want to do like some of the singular value.
Yeah.
Well, how will the sketch work?
You can, yeah, so if you just wanted the sum of the small singular values, you could use a similar approach, which would cost you about the same. You would get the same approximation ratio. In fact, this approach, the sketching approach, preserves all of the singular values up to this kind of slop factor individually. Yeah, that follows from relative perturbation theory in the style of Ostrovsky. Yeah, was another question?
Yes. At the beginning, we were assuming that A was dense and unstructured.
Yep.
If we assume some extra knowledge of A,
Yep.
are there tricks to sort of inform how we would, I don't know, either do the sketch or
Yeah.
do things?
Yep. Okay, so if A is sparse, then there are approaches that are cheaper involving sparse dimension reduction matrices. And so that would be more effective if you have a sparse linear algebra library. It turns out that these things don't work so well. So every time we try and implement this, we are sad. But that's one thing you can do. It's also true that if you know a lot about A, just sampling rows uniformly at random might be enough if all of the rows somehow are contributing equally. So this happens in some problems as well. So there are definitely ways you can prove if you have additional knowledge, even if you don't have full knowledge. The nice thing about these methods that I've described is that they really are agnostic to the matrix. And so I guess one way to think about this is that here we're assuming that it is expensive to multiply by A, and so we design a dimension reduction map so that it's cheap to apply the dimension reduction map. You can dualize this perspective and say, imagine that it's cheap to multiply by A, and therefore I don't care so much about the dimension reduction map. Maybe I would just want to take advantage of the fact that A is a fast multiply. So you can do that for sure. Yeah. More questions? Okay, so there are lots of examples of dimension reduction in numerical linear algebra. And I would say that a significant part of the literature depends on the ideas that I've showed you here. It's a very beautiful approach if you use it as part of an iterative procedure. It can be a very effective way to solve problems. But part of what I wanted to demonstrate to you is that this is by no means the only way that we can use probability for linear algebra. So some of these surveys, again, not naming names, are like, randomized linear algebra is the study of sketching matrices. And I just don't believe that that's true. There are lots of ways we can use probability to solve linear algebra problems. And that's what we've been talking about all week. Monte Carlo approximation, random initialization, progress on average. There are other things that I didn't talk about here. Things like randomized preconditioning, where you use a randomized linear algebra method to compute a preconditioner so that you can solve a linear algebra optimization problem faster. There are methods for placing problems in general position, so transforming them so that you don't encounter algorithmic failure modes like big pivots in Gaussian elimination. People also use this for simultaneously diagonalizing matrices. So you can put the problem in general position so you don't accidentally encounter a bad situation. People use smoothed analysis where they perturb the problem instance a little to make it easier to solve. So these are I'll describe briefly at the end of the lecture notes. But I firmly believe that there is really a beautiful interplay between the subjects of computational linear algebra and probability, and I'm sure that there are more paradigms waiting discovery. And I look forward to learning about those from you. Thank you.